So we are live, Mr. Govind. We'll start. So very good morning to all. It's our great pleasure to have you all for the Knowledge 4.0 webinar series, which is one of the unique initiative of Chennai Institute of Technology under the guidance of our Honorable Chairman, Mr. P. Sriram, a successful first generation entrepreneur, a well-known industrialist, managing director of MK Group of Companies. So under Knowledge 4.0, we have been conducting webinar series such as technical webinar series, research webinar series, career guidance webinar series, and innovation webinar series. Today, we have a technical webinar series named as a role of engineering simulation in the product design, which is going to be handled by Mr. Govind, the product manager, rail vehicle dynamics and NVH at Similia, Germany. So Chennai Institute of Technology was established in 2010 by our Honorable Chairman, Mr. P. Sriram. Now our institute is being within top 10 institutes among all the private engineering colleges in Tamil Nadu. And to say a few words about Mr. Govind, Mr. Govind Mohan completed his engineering from Anna University in 2012 and Master's MSc Computer Aided Conception in Mechanical Engineering in RWTH Aachen University, Germany. And from there onwards, he was continuing his career in Germany as an intern in Fraunhofer and intern and the full-time employment with Void GmbH and engineer mobility simulation in FE Design GmbH. And then he joins Dassault System. Now he is the product manager, rail vehicle dynamics at Dassault System. So it's our great pleasure to honor to have Mr. Govind for this wonderful session. And thanks for accepting our request. And I thank all the participants also. Mr. Govind, over to you.
Thank you very much, sir. Very good morning to everyone. I'll start sharing my screen now. So please confirm if you see my screen. Do you see my screen? Do you see the
Yes, sir.
Okay, very good.
Screen show view, slide show view. Yeah, perfect.
Yeah. Okay. A very good morning to everyone who are listening in to the webinar. Thank you very much, first of all, for joining the webinar. I thought I would take this opportunity to share some of my experience, some of my views on the role of engineering simulation in product design. And I really hope this topic is useful to most of you guys. And let's see, I'll just share my viewpoint on what engineering simulation is and how it contributes to product design. Today's topics will be, I have split the topics into three main parts. So the first part of it, I would cover product design and its evolution. Not just about the product design itself, but also the product design process, how it has evolved over time, over years, over centuries, and how this has led to us, led to engineering simulation itself. And also, I would also connect the design process to the engineering simulation, the need for engineering simulation, and how engineering simulation is used within a typical design process as on date. Of course, I will also cover at the end some career options in the field of engineering simulation, and what could a student do starting, let's say, from the first year or even second year of engineering on to pursue a successful career in different career streams related to engineering simulation. Starting off with product design. So even before going into what product design is or about the product design itself, it's very important to understand the fundamental notion of product. Product could be anything. different people have different definitions of product. There are lots of definitions of what a product could be, but for me it could be anything. It could be a simple pin, it could be a complicated mechanism, which is used in a clock, let's say, or even a bicycle, which all of us use, or even a complete aircraft. So aircraft with lots and lots of systems, electrical systems, mechanical systems, pneumatic systems, and it's a complicated system itself, but still you can still call it a product. So that's the fundamental definition which I give myself for product, and based on which I would define product design and eventually engineering simulation in my following slides. One thing which is common for each of these categories, irrespective of their size, their function, their ultimate purpose, is and also the complexity involved in each of these products, is a form for each of these products and one or more functions which each of these products address to or have. So the form and the function is, for me, is what defines a product, and based on that is the fundamental notion of product, which would be used in when we describe what product design is. Moving on, looking into products around us, we find certain characteristics. For instance, a simple wheel. A wheel is the most fundamental component, mechanical component, we can think of, because it's almost there in any concept of mechanical system. If we see the actual evolution of the wheel, the notion of wheel started off all the way in 8000 BC, somewhere back 10,000 years ago, with a very rough view of wheel, something like this: a stone carved in a circular form, and a hole in between. So that's what they called as wheel, without even having the complete utility for the wheel themselves. So that was the original view of the wheel. This definition eventually evolved, and people started using the concept of wheel for different purposes. So initially it was thought of not even for transport, so it was just used for pottery apparently, or to drive small mechanisms for drawing water out of a well and stuff like that. So that was the initial use case or the function for the wheel. It evolved for another close to 4,000 years to become the form it has. And then eventually it evolved further. In 2000 BC, it looked more like the wheel what we see in a cartwheel today, in a bullock cart, for instance. And it eventually evolved in 1889 to be used close to what we see today, a wheel with a rim and a piece of tire, let's say a hard rubber tire. And of course, the 20th century tires are much more sophisticated, with different kinds of rims and different kinds of performance tires and whatnot. So what we see is the products evolve, they change shape from its initial configuration to another. The wheel designs evolved over multiple centuries, not over a few days or few months or even few years. On the contrast, I took another example of product evolution where we have cell phones. So cell phones started roughly around 1990s, and it has since then evolved a huge way now. Um, in fact, I haven't put in some recent designs, but almost till 2015 we had a very strong evolution of cell phones itself. On the one hand, a mechanical component like a wheel took more than 10,000 years to evolve into certain forms and to achieve the form what it has today, whereas a cell phone, which was a pretty recently invented piece of gadget, evolved quite fast. I mean, in the span of 20-25 years, it has evolved into multiple form factors and also in terms of functionality. So there are multiple functionalities which have been added. So if we think of the initial cell phone or the mobile phone, it was primarily for communication purpose, nothing more than that. And it evolved a bit to accommodate also text messages. That was itself an evolution of the function of the cell phone, which further evolved into touchscreen and smartphones. So smartphones allowed us to not only connect with people with a voice call, but also connect with people in terms of sharing information. So we had link to the internet, and not just internet, we had possibilities of doing video calls, we had possibilities of sending audio messages. So these were also evolution in the function of the cell phone itself, which eventually evolved, and uh, we had cameras in cell phones. So cameras used to be a separate gadget. People used to carry cell phones and cameras separately, but now the conventional cameras don't even exist, and people are quite happy with the high definition images what they get from the mobile devices. So it has evolved a lot from its original version of the cell phone, where the purpose was just to talk to another one in a distant place, to completely now people choose cell phones based on the camera functionality, um, the feature, the extreme list of the explosive list of features it offers, and voice call is not even a priority. So voice call is a assumed part of the device. So that's the level of evolution products can also take, and within a span of very, very short time of couple of decades or little more. So why do products evolve? So this is a very fundamental question we should ask ourselves. So why can't the product remain the way it is? Because the reason why the product exists is because it has it solves a problem basically of someone. And as long as it solves the problem, what does it need to evolve? Well, it turns out the evolution is part of the requirements. So the requirements of what the particular product should do also evolves with time. So people start changing their requirements or their needs or the expectations from the product. So people at the start of the product evolution cycle just think about its core functionality. For instance, in case of the mobile phones, just talk to people. The next step, people say, well, now I can talk with people. Now how safe is it? So, or how reliable is my phone? Can I take it everywhere? Or can I is the voice secured enough between just two people? Or can someone else also hear this conversation? So such kind of requirements pop in next. So the product has to evolve to satisfy these needs also. It evolves further. People think of aesthetics now. So it's not just about the function, but also the look and feel of the product. So how good is my product? Am I happy with it? Am I proud to have owned this product? So such kind of attributes come next. And last but not the least, the performance, and not just about the core functionality. People start looking for value additions like a camera in a cell phone, or the possibility to transfer data by a certain technology, or the wireless technology which is supported by the device, the speed at which the device can process stuff. I want to play games. I want to do virtual reality stuff. So is my device capable enough for that, or performant enough for that? So such kind of requirements also pop in, and all these requirements step by step push the product to evolve and reach the stage what we see here. But why do certain products evolve faster than others? So cell phones evolved in a span of 2 to 3 decades, whereas a wheel had to wait for 10,000 years to get into the more or less a complete form, what we see today. This is this To understand why, what could be a possible reason for this, we have to look into the design process itself. So how was the wheel designed, or who designed the wheel, or how the design itself evolved as a process. In early days, if in case of wheel, for instance, the evolution was more or less a natural evolution process. Someone came up with an idea someday and then made a form, and it was like that for years or centuries together, till someone else came up with a different idea saying, oh, I will just make these modifications and now I can use it for such and such function. So these sporadic ideas here and there, which popped up over years, is what made the product evolve. There was no real standard process or a procedure or a design schema for the product to evolve. So this made the product evolution really, really slow. So the product evolution was more or less an accident until 1760s, where industrial revolution started and people started thinking about ways to use machines and use machines to manufacture stuff. Um, there was a shift in paradigm of producing products from just bare hands by individual people to mass production or producing stuff based using machines. So people have to be efficient to create machines. So they can't go about relying on ideas coming sporadically from people. Rather, they have to set up some process to manage the whole evolution, or to come up with new designs to support new manufacturing processes, which was a big push until 1960s. So still, even after industrial revolution, there wasn't a real design thinking or a very well structured design process as such. In 1960s, there were different approaches coming from different countries. One of the approaches was the Scandinavian approach, quite famous one for design thinking. And this, with such approaches and with such ideologies, people try to standardize the process of design, uh, the complete product design, starting from the gathering of requirements to an end product. And this made huge leaps in terms of new designs um, and more robust designs, because now anybody who has an idea has a structure to work on, and they can push their product designs or validate their product designs by sticking on to this design process, which eventually evolved and took the form what we call as the conventional design process today. So a conventional design process would look more or less like this: a structured design process, a requirement. So someone goes to a customer or a user to gather the requirements, and a concept is prepared in whatever form it's prepared, and then a detailed design is worked upon. And once a detailed design is there, people start creating prototypes, mock-ups, proof of concepts, and these prototypes then are tested. The successful prototypes thrive further. The failed prototypes go back to the drawing table. They are redesigned, reworked, new prototypes are born, and then tested. So this process continues until a satisfactory product satisfying the shape constraints and also the function which the product has to satisfy is achieved, and then it's released. Of course, even after releasing, based on the inputs from the customers or the users, the cycle again repeats, starting from the concept, detailed design, prototype, and testing. Of course, in 2020, we are no more adhering ourselves to these structured design processes or the conventional design processes. Rather, we are thinking about generative design. I would talk about it in one of my later slides. We would not go into detail about it, but it's a completely different paradigm as well. The way in which the design itself orchestrates itself. A structured design process would start, as I said, from a requirement stage, move on to a concept stage. A concept stage is when people are not looking for real details. So they know roughly about, okay, this is my function, this is my space constraint, and what should it do? For instance, let's say a car. A car is something, how do I define the function of a car? It has to transport people from one place to another. There is no form requirement as such. People might say, well, I need to transport 4 people at a time, and to drive the car, it should be intuitive enough. It shouldn't be like driving an aircraft or something. It shouldn't be so complicated, and safety should be ensured. And driving, there should be reliability, that if I can, I should be able to rely on the product, that when I if I want to travel from place A to place B at any given point, I should be able to do it without having to think whether the device would work today or not. So these are very fundamental functions which people have in mind while having early, let's say, early concept stage view of the product. This is a very early stage of the design process, let's say. In a detailed design process, you can't just work with the concepts, but rather you have to put in um, very detailed designs which actually work. So this is when people start thinking. For instance, for a car, in our example, we might think of having wheels. Should the car roll on the road? Should the car fly? Should the car what is my terrain of operation? So am I operating on waters, on land, on air? Depending upon what I think I'm operating, let's say I operate on land, which is what a typical car do. So I need wheels to roll on the road, and then I need a structure. So I need 4 people to I have 4 people to accommodate in my design. So where do I place the seats, and who drives the car? Will it include the 4 people, or will it be an extra person? What is the driving concept? Do I have a driving wheel? Do I have a button which I just click on and the car starts? Um, and so on. And what is the locomotion? So whether I use an engine, whether I use a motor, or however it is. So these are some kind of considerations which are put in during the detailed design phase. Moving further, now comes the fun part: making prototypes. So you have the detailed design on the paper, or on your computer. Now you want to do prototypes, so now you go into real world. You make mock-ups. So these mock-ups may not have the real material, or may not be used by real customers. Rather, it's just a proof of concept to see whether our detailed designs, or which of the detailed designs actually work and which fail. So this is an interesting step, because moving from an on paper design to a prototype is not a trivial task. So because at the prototype stage, you'd have very limited resource in terms of what materials you can use and the manufacturing facility and so on, because the product itself is not proven. Without a proven product, nobody would invest on a manufacturing facility. So basically, people would try to find materials and resources as they find fit for this product, and try to create a proof of concept. This is where a lot of innovation, lot of experience, and lot of teamwork is required to build these prototypes which actually work and give you a real world um impression of the product, how whether it would work or not. Then comes the testing. So a more high fidelity prototype is promoted onto a testing phase, where people just test the product as it is in real cases. Maybe there are sample users whom we take in, and they might also be involved in the testing depending upon the product we are working on, and so on. Then finally comes the design release phase. So that's the phase where your product sees the real world, and gets tested by real users. Of course, in the product design process, we can split it into um, two parts basically. So one, the concept design stage is more to do with the form of the product. So how it looks, the shape of the product, how the space of the product is, and so on, which is mostly done in a conventional design process using design drawings. So most of the engineering students, irrespective of the department they have chosen or the field of specialization, would have taken this course, engineering drawing. That's pretty much what people used to do, at least in a conventional design process. They take a piece of paper, use their pencils with their complicated compass arrangements to really come up with these designs. And then the function part, where prototypes are built with materials, and also the testing. So you have to design the tests, and also put your prototype onto test. So on a very fundamental level, we can we can categorize the design process into two main aspects. So one is creating the shape or the form of the product, and designing the function of the product. um, with advent of computers, this cumbersome product process of using engineering design, all of us know how difficult it is to get the lines correct, to get the measurements correct, and to imagine a 3D object in 2D. So if we have so much difficulty, or if we make, I mean, I'm pretty sure not all of us get 100 out of 100, or the full marks in engineering drawing. All of us are reasonably good engineers, but still we do make mistakes. And we make mistakes on very simple solids like prism, or a very simple primitive solid shapes, because it's not very intuitive, or it's a bit of a difficult task to imagine a 3D object and its 2D projections in different planes, and representing them in engineering drawing. Because of the inherent nature of this technique, there are a lot of human errors involved, and this could also lead to wrong products being designed, and also lead to a lot of frustration because you have to redesign the product and you don't realize it in the early concept stage, rather much later. So a concept designer would have something in his mind, but a detailed designer would understand it in a different way. A prototype engineer or a test engineer would understand it in a completely different way. So to align all these people together, it was very difficult. Using of computers revolutionized this complete process, so made the complete process digital, so people don't have to really go through this whole pain of converting a 3D geometry into 2D and representing it in a piece of paper. Rather, they can use a CAD model, so which we call as computer aided design, or a 3D representation of the real-time object, which is very intuitive because every object what we see is also 3D. A similar thing also applies to prototype and testing, because prototypes, as I said, are a tricky business. We don't get the manufacturing facility upfront, so we have to work with the material and resource what we have at that given point in time. So it's very, very hard and sometimes very costly process. um, Imagine a complete car, or even an aircraft, let's say. If you were to do a prototype of a complete aircraft and test it, first of all you have to design the test which is safe enough without harming people involved in the test. Even if you manage to do that, if the product fails, imagine the amount of cost incurred in the in the failed concept. So how many times for such a complicated system like an aircraft, or even a complete high speed train, it takes so much iterations, and each prototype would cost you in millions. So this would literally make the complete product non viable to bring into market. To avoid such problems, of course, again, the computer aided technology revolutionized the whole process. And we have something called as computer aided engineering, or I call it engineering simulation, because engineering can be many more than what engineering simulation is. So general terminology is, of course, computer aided engineering. So CAD and CAE, we call it. So these two digitalization process of the design process, digitalization technologies of design process completely changed how we think about a product design. A typical engineering simulation. So now I move into the second part of my presentation, where I dive a little bit deep into engineering simulation itself. Engineering simulation is nothing but represent is a process of predicting how a particular product would perform or function in reality without having to really model it in real life, like making a prototype. So you digitally model the component or the complete product and simulate it based on the underlying physics principles involved in the design, and try to predict whether or not the product would be successful, and if it's successful, under what conditions and stuff like that, to get more insight into the product without getting our hands dirty, basically. A typical engineering simulation process starts with, of course, the physical system, concept design in this case, let's say, and then we build a detailed 3D model of it, or even a logical model sometimes would help. So a logical model would be like a representation of a spring and a damper, for instance. So you don't have to really model the detailed definition of springs and dampers, but you just have a notion of spring and damper. You logically represent these two aspects in simulation. The most important step is to derive the mathematical model, which describes the function of the system. A mathematical model is nothing but the governing equations or the physics under which the physics which governs the functioning of this body. For instance, a simple, let's say, it could be simple physics from the second law of Newton's second law, or equations of motion, in other words, or it could be a very complicated physics like fluid dynamics, a flow of fluid across within a tube, or of a complete weather prediction physics, or it could be any kind of complicated physics. And all these physics are at the end represented by a set of governing equations or mathematical equations. These equations describe the function of the object. The next step would would to use these equations to solve the physics problem underlying. So you would ideally have algorithms which work on these equations, and these algorithms are written, are embedded in softwares, simulation softwares, and the equations are inbuilt in these softwares as well. So what you would ideally have in real world is a CAD representation of the real system, and this would be given to the simulation software, and the simulation software would, with whatever technique it uses, creates the fundamental physics equations which are relevant for this physical system, and these physics equations are solved using special algorithms which are tailor-made to solve these set of equations. Once we solve the physics behind it, we have a reasonable prediction of how the system would behave. For an engine, for instance, in this case, whether the engine would work as we expect, whether it will provide the sufficient power, whether it will be durable, will the parts break or not. So such kind of predictions can be made with simulation by solving just the fundamental equations underlying describing the physics. So this is a enormous power what engineer could dream of. So even before a physical system is manufactured or exist in reality, you can predict whether a particular system would work or not. So this hugely saves time in terms of the prototypes and testing you have to do, and also to account for scenarios which are very hard to test in reality. Um, how do you test car crash? So you can test it, there are testing facilities today, but still it's a costly process. How do you test aircraft from failing, or such kind of complicated scenarios cannot be tested, just cannot be tested. So you have to rely on engineering simulations for also capturing these use cases and these test cases. So moving on, this is just a concept illustration of what I mean by simulation. So you see this ball moving, just a ball with the initial velocity, taking a trajectory under gravity and landing somewhere else. So all of us would have studied, or most of us would have studied, at least in the school physics, how to model this, how a mathematical model of it looks like. It's simple 2D equations of motion from the fundamental physics, from Newtonian physics, what we studied. Well, let me make the problem a little more complicated now. So the ball just doesn't start and end at a point, but it bounces and bounces again. So there is a contact with the ground, and you can also see, well, it bounces, but when it, after the bounce, it doesn't have the same amount of energy for the next leap. So it actually travels less distance and also travels less height. Interesting. So how do I capture this physics? So add few more I add little more complications or little more sophistication. Uh, we can also call it detail in terms of equations of motion or the mathematical model. So this mathematical model now describes this phenomena, not just a ball being thrown from one side and lands on the other side, but bounces and does something. Let's make it even more interesting. Let's look at it in 3D. So how would it look like? So now we are not just dealing with two-dimensional space, but a three-dimensional space where the ball can move not only in one direction, but in not just in the longitudinal direction, but also in the lateral direction. And also the ball can turn. It can rotate as it moves. So in cricket we call it swing, so it can also swing in air. So such kind of complications, such kind of uh, details can also be backed in, but then we have to just account for it in mathematical side to add more and more equations to represent it in a more realistic sense. As I said, we can consider the interaction of the ball with the surrounding air or the atmosphere. Then we have to add the Navier-Stokes equation to describe the fluid motion and the fluid-solid interaction phenomena. We might even consider adding thermodynamics in a very, very accurate level. We might think, okay, the temperature changes now, and because of the temperature the air within the ball changes or the air around the ball changes, so the density changes, which will also affect the trajectory and the friction offered to the ball. So now I add thermodynamic equation to it. I go one more step further. I say, well, during the contact, I just don't want to consider the normal contact, but also the friction behavior of it. So then I have one more level of detail added. So we can keep adding details of different level of details and different make the mathematical model more complete. But what is the point? The point is, it depends upon the user. So if I'm quite happy with the first case where just a ball moves, I'll go back to the slide. If I'm just happy with just the 2D case, all I'm interested is to know where it would land. So what is the distance? So if that's my design criteria or design requirement, I'm quite happy to just live with this set of equation. But maybe my requirement is to see how much the ball bounces after the first contact or subsequent contact, or when will the ball stop. Then probably I should consider this level of detail. If I want to really consider how is it positioned not just in the longitudinal direction but also in the lateral direction, then I have to consider these equations. But if I really want to go into detail of how the ball turns or twists from the perspective of the ball, but not from the perspective of the global system, then I have to consider all these equations. So depending upon what the purpose is, we have different simulation domains. So the equations, basically, the underlying governing equations, are classified into um, certain domains of simulation, which solve certain sets of equation. For instance, multi-body dynamics. Multi-body dynamics just assumes the body to be rigid, or any object to be rigid, and it doesn't consider any elasticity of the object. And all what we are interested with the multi-body dynamics is the overall dynamics, overall system characteristics of the complete system we are considering. For instance, in this case, the ball, I am just interested how the ball moves. I'm not interested whether how the ball deforms after its first contact or first impact on the ground. Structural simulation, on the other hand, says, no, 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 I'm interested in little more. I can't assume the ball to be rigid. I want to really consider the flexibility of the ball. Then you have to consider a more detailed analysis, let's say finite element analysis. That's the structural simulation, where elasticity of the body is considered. Well, there are also other kinds of simulations. Electromagnetic simulation. For instance, we have our cell phones, whether the electromagnetics, the electrical circuits within it work properly. To simulate that, we have different sets of mathematical equations, and it's categorized under electromagnetics. Similar thing applies to thermodynamics, fluid mechanics. If you are looking at fluid interactions and fluid structure interactions, and just the pure fluid interactions, mixture of liquid and air, such kind of problems. Control systems. There are always control systems all over the in any system, in any modern system. What we see, a cell phone, a car, everything has electrical control systems which control different actions or the electrical circuits. We can these are separate set of equations. So the simulation domain basically splits all these equations into different domains, and each of these domains can be used together. So depending upon the level of detail what we want, we choose one of these or more of these. So that's the idea. That's why that was also the reason why we have simulation domains. Some industrial applications. So enough of talking. Let's look into some industrial applications. I'll play some video. So that was kind of a demonstration of how simulation manifests itself in real life. So you saw, starting from design stage, from simulation, you have custom testing scenarios, you have correlations, you have virtual reality experiences, and so on. There is another video. The next video I would play is it's a completely different application. So we shouldn't think simulation is just for automotive or for mechanical applications, but it's all over the place. So this is just a example, one of those examples. This was again a demonstration of a completely different application and how impactful simulation could be. And this is reality. So this is the Living Heart project in Simulia has been there for almost a decade now, and we could realistically simulate heart functioning and also assist in medical device manufacturing, in not just for heart, for different human being organs. I will switch back to my slides here. There's one more interesting aspect of simulation, how things are evolving. So the conventional design process, as I explained before, is with CAD, then followed by simulation, then testing, partially testing. So simulation tries to replace testing mostly, but still there are still some testing required for approvals, design approvals, followed by the release. But then there is a new paradigm shift, which is current, which is the simulation driven design. So you don't put simulation after CAD, rather CAD and simulation go hand in hand. So the iteration loop is much faster, and you come to a realistic solution much more faster compared to the conventional design process. There is also a demonstration of that. I will just show that.
Your design team faces an impossible task every day. How do they create new designs that won't fail without information on how they will perform? Simulation experts can help, but their feedback often comes too late. As a designer, wouldn't it be great to know how a design performs as you are designing it? The age of simulation-driven design is here. We are now in an era where simulation is being used to synthesize and define the physical design, rather than to simply evaluate and validate final designs. Imagine getting immediate feedback on the performance of your part as you are designing it. Realize how much better your design could be and how much faster you could deliver it. Think of how you could confidently turn around a customer's engineering requirements faster than your competition and win more business. Envision the ability to create lighter, radically new design concepts with full confidence that they will exceed performance targets. Innovative manufacturers are taking advantage of advances in simulation technology and development processes from Siemens PLM software to beat their competitors to market with higher quality, longer-lasting products. Come visit Siemens PLM software to learn more about the new age of simulation.
That was another demonstration of how the industry is evolving, or in which direction the industry is evolving in terms of product design and simulation driven designs. So I'll switch back to my presentation in the last slide now, pretty much. The career options. So simulation, yes, it's cool, we can do a lot of things, but what can a student do? So there are, as I see it, there are
Wi-Fi
three.
cut ஆயிடுச்சா?
Sorry, can you hear me? Or
Yes, sir. We can able to hear you, sir.
okay, good. So again, the career options. The career options itself, we have, as I see it, we have three options. You can be an academic researcher and a simulation academic researcher. And simulation academic researcher would typically work on the physics equations. So a realistic, you have the realistic physical system and how to represent the realistic physical system in terms of equations. That's what an academic researcher would work on. A software developer, who is in between the user and the researcher, takes these equations, converts them, finds algorithms to solve these equations, and creates software programs which can actually solve these problems and present the results to the end user. The third career option is application engineer. Application engineer actually uses these softwares to solve real world problems. So he is the one who about whom we have been have presented for most part of my slides. So that's basically the third option of the career. Uh, I see sensibly organized. The application engineer could be part of a OEM or a big company like a car manufacturer or a aircraft manufacturer, or the application engineer could also be part of an engineering consultancy which actually provides um, uh, engineering solutions to big companies. So all the three career options are available, and much many more. As I said, the industry simulation technology caters is pretty wide. It's not just restricted to transportation mobility or automotive or aerospace or even industrial equipment. You can go into healthcare. So it's very hard to say that recession will affect this kind of a profession. So this is also a unique advantage what this career offers. I just have one last video and I'm done with that.
Behind every good product, there's a great story. Some of the chapters are obvious, but many are hidden. These are the unseen forces that can mean the difference between failure and success. And often, they can't be understood by traditional methods. That's where we come in. Digital simulation allows us to perform comprehensive tests in a virtual world, discovering insights throughout the design lifecycle, so you can develop the perfect parts, assemble them into something completely new, and discover new ways to improve lives, all before a single product gets built. In this way, we can mitigate risks, enhance innovation, and change the world together. This is our passion, our legacy, our story. Simulia. Reveal the world we live in.
Yes, Mr. Govind. Can you hear my voice?
Sorry, yeah, I was muted.
Yeah.
So that was my last video, last presentation slide also. Thanks for the opportunity. Thanks for listening in, and hope I have shared some useful information.
Yeah, Mr. Govind. Really, the session was more informative. I hope everyone have learned something, and you have given a clear insights about the simulia and what we think about the simulation, what will going to be used. But you are thought about the beyond what we think, and really, it's more like useful for us. And not to with this, we have few questionnaires also, and I'll just go within the questions. So the first, I got a question. So can you explain the difference between the MATLAB and Simulia? What is the difference between these two?
MATLAB is a generic. It's a different product, different kind of a product. MATLAB is a generic software for solving mathematical equations, but Simulia is a more matured product for doing engineering simulations itself. So um, if you were to use MATLAB, you have to write your own equations. First of all, you have to find these equations yourself, and then write these equations in terms of MATLAB program and kind of execute them also. But engineering simulation software like Simulia would have the physics and also the equation solver inbuilt in it. So the user would not have to really think about the equations, the underlying equations itself. Rather, they just have to say what kind of physics they want to model. They want to consider the elasticity of a body, they want to consider the body as rigid, or they want to consider the fluid aspect or electromagnetics. So they just have to choose the physics basically, and the equations are automatically um, you know arrived at and also computed by the software.
Yeah. Uh, Thank you. And we have another question from Ms. Preeti. Can I know the app which is easy to use on simulation? If it is,
App
yes,
application, yeah.
yes.
Okay,
App.
so that's the Simulia. So Simulia has lot of its products. Depending upon the physics we cater to, so we have different kind of products. For let's say for multi-body simulation, we have Simpac. That's the product we offer, and for finite element analysis, we offer Abacus. That's a product, and so on. So if you go to our website, I think you would have enough information on what depending upon the simulation domain you choose, we have different application.
Yeah. Thank you, sir. And another question we have: Can you from Mr. Tirumurthy? Can you suggest any simulation tool for control system analysis? And what is the probability of these tools to getting obsoleted and being replaced by any other approach?
Control systems are simulation domains themselves, so I don't see them being obsolete, getting obsolete. um, any software, for instance, one of our company products is Daimola. So that's the product what we use for control system modeling. And MATLAB Simulink is also one of the famous products which is used for control system modeling. So these are some of the softwares which are used for control system modeling.
Yes. Uh, and we have one more impressive questions, like, can we have simulated human emotions?
No, I don't
No.
think we have reached that stage yet.
Yeah.
Hopefully not.
Okay.
We would never reach
Okay.
that stage.
Okay. And uh, actually, Mr. P. Shanmugam, Prabhu, what are the main objectives in software simulations? As already Mr. Govind have explained in the previous questions, and we looking for another questions. Sir, Mr. Kriti Rajan, how simulation is required in academics research? I hope this is the last question.
Okay.
How simulation is required in academic research?
So academic research is in fact the most appropriate place, or simulation can be used to the to its most of its advantage, because industry is normally, as I explained in one of my slides, for prototyping and for testing new design concepts. At least they have some resource, they have some financial backing, which is not the case for academic institutions. To get funding for no designing or for doing prototypes is a very very difficult task. Simulation is an easier way. So without even having to invest so much money on the new designs or new concepts, you can virtually model all these new concepts and simulate them. So which is a huge power. It's a powerful tool, powerful technology by which you can create extraordinary designs, innovative designs, without even having a huge funding like an industry has. So this is where I see simulation is even more important for academic institutions.
Yes, and Mr. Govind, we can coming into the end of the session, and I would like to give a big thanks to you for this wonderful session. And once again, this session is really more informative for all of us, and it give clear thoughts about the Simulia. And also, I would like to thank to our chairman, Mr. P. Sriram, so who giving this opportunity to open the community with a lot of knowledge sharing with the Knowledge 4.0 webinar series. And thanks to management. And thank you everyone for the participants for your being patient and listening and your valuable comments. And we'll share you the feedback form to your email, registered email, and the certificates to you. And keep on watching with us. Stay tuned on Knowledge 4.0 webinar series. Every day we have a different resource persons with the domain expertise, and looking forward. Thank you everyone.
Thank you guys. Thank you for listening in.